let us now make a list of what are the possible symmetry operations can be there. So, we have already seen some of them. So, we have seen, for example, rotation, and we define the fold of rotation also, n-fold rotation, which is defined by theta min is equal to 360 by n. So, when we say fourfold rotation, theta min is 360 by 4, that is 90 degree. So, minimum rotation by which it will come into self coincidence is 90 degree. If that is the case, we call it a fourfold axis. Minimum is required because see, if it comes into coincidence by 90 degree, 90 degree applied 2 times is 180 degree, and in 180 degree rotation also it will come into self coincidence. So, a square comes into self coincidence by 180 degree rotation also. So, if you do not be specific of theta min, but just theta, so you will say 360 by 2 is equal to 180 degree. So, a square has two-fold symmetry. It does have two-fold symmetry, but as a subgroup of fourfold symmetry. So, for actual description of its symmetry, we will say that it has a fourfold symmetry rather than saying twofold symmetry, because it has twofold symmetry, but it is not a complete description of its symmetry because it has a higher symmetry. So, that is rotation, and so that is, so you have a rotation axis. The point symmetry that leaves at least one point fixed. So, like rotation. So, rotation leaves the axis unchanged. So, rotation, the points on the axis are invariant. Then reflection, points on the reflection plane are invariant. These points do not change after reflection. But if you talk of space symmetry, if you talk of translation, then all points move. For translation there is no fixed point. So, that is a space symmetry. So, rotation is a point symmetry, reflection is a point symmetry, but translation is a space symmetry. Similarly, glide, we will come to that, that is translation plus reflection. Or we have a screw, which is translation plus rotation. So, since they have translation component, these also will not leave any point unchanged, invariant. So, all these are space symmetry operation. So, rotation, since it is a point operation, it leaves points fixed, and we know that those point fixed are what is the called the rotation axis. So, those are the fixed point. And in terms of, we define group. So, when we say a rotational symmetry groups, so the symmetry group nomenclature, there are two of them. One is the Hermann-Morgan. I think we had discussed this, and the other is Schoenflies. So, the Hermann-Morgan notation is 1, 2, 3, 4, 5, 6, just the number. The fold, the n fold is used as the representation of the group itself. So, n-fold rotation is actually a symmetry group, a fourfold rotation is a symmetry group, and that symmetry group itself is represented by the letter 4. So, 4 takes a different meaning in this notation. It is not just the number 4, but it is the name for the symmetry group of fourfold rotation axis. So, and the corresponding Schoenflies symbols are just with C. If you write C with 1 as subscript, so C1, C2, C3, C4, C5 and C6, this becomes the Schoenflies notation. So, and C stands for cyclic. So, Schoenflies tries to tell us that these are cyclic group of order 1, cyclic group of order 2, whereas the Hammond-Morgan notation, it's you just have to know that it is cyclic and only the order is given. So, let us say C4, the Schoenflies notation. So, either you call it C4 or you call it 4 is actually a symmetry group of rotations. And what are those rotations? So, you had theta min is equal to 90 degrees, but then 90 applied by 2 times 180 degree also should be in the group by the group property, that combination of any 2 operations also has to be an operation. So, that is 180 degree. Then 90 further applied is 270 degree. So, that is also should be part of the group. So, instead of rotating by 90 degree, if you rotate by 270 degree, still the square will come into self coincidence. And finally 360 degree, but 360 degree rotation is equivalent to no rotation because points come to the same place. So, this is what is the identity operation of the group. Every group should have an identity, you know that. So, if you make a table, the Cayley table or the group multiplication table, so you can write, you can use different symbols. So, for example, for 90 itself, so see there is a little, so little confusion can be there here, but context makes it clear. If I write for operation 4 as an operation, then it is showing as it is should be interpreted as a 90 degree rotation. So, I have 4, then since 180 degree is a twofold rotation, I can call it 2. 270 degree rotation, so 270 degree rotation is equal to minus 90 degree rotation. You get to the same location. So, 270 is nothing but inverse of 4. 270 is inverse of 4, or sometimes you can call it 4 plus, so you can call it 4 minus. And 360 degree is identity, we call it 1. So, let us call it 4 plus 2, 4 minus and 1, and here we have 4 plus 2, 4 minus and 1. I have gone little bit unconventional here. Usually one starts with identity. So, identity usually is the first element in the row, both the row and the column, but does not matter, this will also work, and then you just multiply and get your table. So, 2 times 4 plus and 4 plus, 2 times 4 plus, that is 90 plus 90, 180, so that becomes 2. 4 plus and 2 is 90 plus 180, 270, so that is 4 minus. And 4 plus and 4 minus, plus 90 and minus 90 is an identity. So, they are the inverses, and then 4 plus and 1 is 4 plus. Similarly, you can complete the table. So, 2 and 4 plus will be 4 minus, 2 and 2 will be identity, 2 and 4 minus will be 4 plus, and 2 and 1 will become 2. So, inverse of 2 180 degree rotation is itself, because 2 combined with 2 gives you the identity. So, it is a self inverse. So, you can say 2 inverse is equal to 2. 4 plus inverse is 4 minus, and 4 minus inverse will become 4 plus. So, that group property that every element should have an inverse is being satisfied. So, you can complete this. So, you will get 1 here, 4 minus and 2 will become 4 plus, 4 minus and 4 minus will become 2, and 4 will become 4 minus. And identity of course will leave everything unchanged. So, 4 plus 2, 4 minus and 1. So, that is the so called Cayley table. Why it is called cyclic group is that in this group I have an element which, in terms of which all other elements can be expressed as powers of that element. So, 4 plus is 4 plus to the power 1 applied 1 times. 2 is 4 plus square. 90 degree followed by 90 degree is 180 degree. 4 minus is 4 plus cube. 90 plus 90 plus 90 is 270, which is 4 minus. And 1, the identity itself is 4 plus raised to the power 4. So, 4 plus is a element whose powers give you all other elements of the group. So, this is what is defined as a cyclic. A cyclic group is a group in which all elements can be expressed as powers of a single element. So, in rotation this will always be true, but you will see, we will see other groups where this will not always be true. So, all the rotations. So, the rotation groups, the possible rotation groups are infinite. You can simply keep writing your integers. All positive integers correspond to a rotation group. And the order of the group is the number of elements in the group. So, that is also the same as the integer. So, how many rotations the Group 4 had the 4 rotations, 4 plus 2, 4 minus and 1, or 90, 180, 270 and 360 if you so wish. So that is the order. So order is the same number. So Hermann-Morgan notation of these groups are just the order of their group. The subscript in Schoenflies is again the order of the group. We can have roto inversion. The second type is roto inversion axes. So in the roto inversion axes, rotation followed by an inversion. The notation here is n bar. So 1 bar, 6 bar. So n-fold rotation axis always indicates rotation by a minimum angle. N-fold roto inversion axis will indicate rotation by that same minimum angle, but you do not have to stop there, it is followed by an inversion process. So let us look at the one-fold rotation roto inversion axis, 1 bar. So if I have this as the 1 bar axis, and if I have a point, then by how much I have to rotate? 1 bar axis means rotation by a complete 360 degree, which is equivalent to no rotation. So I come there itself, and followed by an inversion. Inversion requires a center. Inversion requires a center on the axis. So I have to identify a point also on the axis, then only it will become a roto inversion axis, otherwise it will remain a rotation axis. So a roto inversion axis has an axis with a point. Now if I rotate this blue point by 360 degree and then invert it into this red inversion point, inversion means taking the point to the inversion center and going in the opposite direction, or continuing in the same direction by same distance. So if this was a distance d, this is further distance d, and then this point, the point which is generated is the image point. So this is the original point P, this is the image point Q. So this is called, this operation is called inversion. So since 360 degree rotation was an identity, so that didn't do anything. So just for the namesake we said that rotate by 360 degree. If we would not have said rotate by 360 degree and said just invert into the point, invert in the red point, so I would have still got from P to Q. So the operation is equivalent to 1 bar is just is equivalent to an inversion center. And rotation axis is superfluous here, because that actually plays no role, because even if you would have taken some other axis, let us say some other axis, and rotated 360 degree about that axis, again you will come to P. So which axis you are rotating about is really not important. So it's not really an axis, it's just a point. So 1 bar axis is really an inversion center, it's just a point. So, we will use the designation 1 bar, but we will not draw it as an axis, because drawing axis is superfluous, and we will always draw it as a point, although we may call it an 1 bar axis. Twofold roto inversion axis is also interesting. Now consider a point. Since this is a 2 bar axis, so it is an axis and there is a center. There is a center, and you now rotate by, since it is a twofold, you rotate by 180 degree, and after rotation you invert. So, just like rotation does not change the handedness, but inversion changes handedness. Inversion is type 2. So, of course, a point does not have an handedness, but you can think of that there was a left handed object there. So, after inversion it will get converted into a right handed object there. Can you think of any other relation between this L and R? So, instead of doing all that operation, if you would have done just start from this L and reflect in a mirror plane which is perpendicular to the axis and passing through the center, you will get the same phenomenon, exactly the same point and same handedness change also. So, a left handed object goes to right handed object by mirror plane. So, twofold roto inversion axis is nothing but a mirror plane passing through the inversion center. So, 2 bar is usually be written as M. We will usually not write it as 2 bar. So, the common symbol is M. If you write it as 2 bar, nobody can say that you are wrong, but since it is equivalent to mirror and mirror is easier to imagine, so this is the common symbol. And common symbol in diagrams, in 2D diagrams, is a line, graphical symbol. Graphical symbol is line, letter symbol is M. Or written symbol, you can say written symbol is M and graphical symbol is a line. In 3D there is some difficulty, that because it is a plane, so it is not a line. So, but usually in 3D we will have the orthographic projections. So, in orthographic projections, either our mirror plane will be parallel to the projection plane, in which case you show it like this. So, in the corner of your projection, in international table you will see sometimes something drawn like this, then you know that the projection plane is a mirror plane. And if in the projection you are seeing a line like this, then you know that a mirror plane perpendicular to the projection plane. So, let us discuss threefold roto inversion. As the name suggests, this is a threefold rotation. Threefold rotation means rotation by 360 degree by 3 is equal to 120 degree. So, a rotation of 120 degree followed by inversion in a point on the rotation axis. The two operations, the threefold rotation and the inversion, are commutative. So, they can be inverted also. So, this process is also equivalent if we do inversion first. So, we can say inversion in a point followed by rotation of 120 degree about an axis passing through the center of inversion. So, the two processes equivalent, whether we do the inversion first followed by rotation or rotation first followed by inversion. Also, you can see that this is a type 2, this is a type 2 operation, which means that it will change the handedness of the object. And this is because rotation does not change the handedness, but when inversion is done, handedness change. So, a left handed object will become a right handed object and vice versa, a right handed object will become a left handed object. So, let us look at this process stereographically. So, we draw a primitive circle and let me draw the three reference lines at 60 degrees, so as to guide me in my rotation, and start with an object, let us say a left handed object. Let me draw a left handed object in blue, and I am using a point or a closed circle to represent an object, a right handed object above the plane, above the equatorial plane. So, this is a right handed object and this is the first position, a starting position. So, let me call this 1R. Now, the first operation which I have to apply is 120 degree rotation, and of course, we have to be concerned about the sense of rotation also, and positive sense is anti-clockwise. So, let me take it 120 degree anti-clockwise rotation. So, that is 60 and that is 120. So, the object reaches there, remains right handed at the moment, but I have not completed the threefold roto inversion operation, because this has to be followed by inversion. And here we are considering the inversion in the origin, and we are assuming the inversion, the rotation axis to be vertical, that is in the stereogram the rotation axis is at the center. So, this is an intermediate stage in the journey, 120 degree rotation. After this, I will invert it in the origin. So, it will go there after inversion, and since it was above the plane, now it goes below the plane, and since it was right handed, by inversion it will become left handed. So, to show left handed I use red color, and to show that it is now below the plane I am using an open circle. So this is the second position, and I now have a left-handed object sitting there. So this is one operation of threefold roto inversion. If I apply this roto inversion again, so you can see I again come 120 degrees, so I come somewhere there and then I invert. So I go there and I started with a left handed object, inversion again changes it, so it becomes a right handed object. So I again use the blue color, and from below the plane inversion will bring it above the plane. So the next position is 3 are there. So now you have got an idea. So as I operate again, then 4L will come there, 5R will be there, 6L will be there, and finally you will come back to 1R. So that will complete the operation. About the axis, there is a graphical symbol for threefold roto inversion, and so let me place that at the center of the stereogram. The graphical symbol is a triangle, a filled triangle, but with a hole left in the center. So I fill the triangle except the central hole. So that's the graphical symbol of the threefold roto inversion axis. Fill triangle with a hole. So the hole actually, why this symbol is being used, the hole in the center of the triangle shows the threefold axis. So you can see everything is related by the threefold axis also. The threefold roto inversion axis includes threefold axis as its subset or subgroup. So you can see the 3 blue points above the plane are at 120 degree. So they satisfy the threefold symmetry, and the 3 red points below the plane are also satisfying the threefold symmetry. So it has threefold symmetry as its subgroup, and hole in the center shows an inversion center, represents the inversion center. So you can see that all points are related to each other by a center of inversion also. So for example, if I take 1R point and invert it in the origin, I will get 4L. From right handed it will become left handed. So from blue it becomes red, from above the plane it goes below the plane. So these 2 points 1R and 4L are related by a center of inversion. Similarly, 2L and 5R are related by center of inversion, and 3R and 6L are related by center of inversion. So the 3 bar axis, I can, so another symbol for the text symbol for this is, the text symbol is 3 bar. Let me write it. It's like graphical symbol. We have a text symbol. With 3 bar. And what I showed you, that 3 bar is nothing but a union of, or a combination of, a threefold axis and a center of inversion, which I represent by 1 bar. Now you have got, you should have got a hang of it. So a fourfold roto inversion you should not have any problem. 4 bar is now easy. Start from a general point there So, these blue lines are not symmetry lines, these are just reference lines for me to help me rotate. So, since this was left of this line, a 90-degree rotation brings it here, inversion will bring it there, but take it down and change the handedness. Change of handedness red, going down, circle, open circle. Then again a 90-degree rotation and inversion from down comes back on top, changes handedness again, so becomes blue. So, both blue are right and both red are left. So, then the next you will get the red here. So, you can see that these two lines will be 90-degree apart. So, just like in the threefold roto inversion you had 3 points and 3 points and twisted, in fourfold roto inversion you have only 2 points and a 2 points 90-degree twisted, but vertically downwards. So, that is a fourfold roto inversion, 4 bar, and the symbol for 4 bar is, you can see that the 2 blue points satisfies two-fold rotation, 2 red points also satisfies two-fold rotation. So, if you just do not think of fourfold roto inversion, you will think that it is a two-fold axis. So, two-fold is part of a fourfold roto inversion. So, the symbol also is made like that, that what you do is draw a square was for fourfold. So, you draw a square, but inside a square you draw lens for twofold, that since it is a twofold is complete, but the fourfold is not, it is a fourfold roto inversion, but twofold is subgroup of that. So, the symbol becomes this, a square with a lens inside, diagonal, a square with a diagonal lens inside and the lens filled. So, that is the symbol for fourfold roto inversion. If you, an object which has this symmetry is a tennis ball, lawn tennis ball. Lawn tennis ball with its lines marked on it. If you try to see with the lines marked on it, it will have a, no other object comes to my mind which will have this symmetry, means familiar object, but crystals of course have such axes as part of atomic arrangement. Thank you.